Casey is going to talk about FRBs and about the Realfast project at the VLA, or JVLA, should I say. I'm sure many of you have heard of them. There have been very exciting developments in the fast radio burst recently over the last few years. And I'm particularly interested because I was involved in finding the first repeating FRB, which did come eventually with the localization. So I'm particularly excited to hear what Casey has to say about Realfast, about what's going on over there. And I will keep an eye on the participants window. So with raised hands, Casey, would you like people to save their questions for the end, or would you like me to point out to you when someone has their hand raised?
If you could point it out, that would be nice. Yeah.
Okay. So yeah, just use the raised hand feature, and I will then point it out to Casey. And with that, I'll hand it over to you, Casey.
Okay, great. Thank you, Adam. So let me just do the most important thing here first, which is share the screen properly. So does that look right to everyone?
Yes.
Okay, great. Yeah, so thank you for the invitation. You know, haven't been active in sort of reaching out to the collaboration until recently, but I know a lot about the area that SCIMMA is pushing, and I'm a big fan of people who are at that sort of interface of the data and the computing and the software. And it's an area that I've certainly thought a lot about. Realfast is a commensal data analysis platform that's been integrated, and computing platform that's integrated with the VLA. And so a lot of the themes that you all think about here in this group are reflected there. I think there might be some more thought on the radio side about high throughput computing rather than sort of flexible computing. But I do think that we're at the point now where the quality of data that radio telescopes produce are high enough that we can think more about sort of the aggregated data sets like catalogs and things that are better connected to what and alert systems that are better connected to what you think very carefully about, which is sort of downstream. So that's one of the themes I wanted to emphasize here for you, and hopefully get some feedback from you in how, as the radio field and radio telescope analysis pipelines mature, how we can better integrate those data streams with SCIMMA and concepts. So that's one theme I'd like to push today. And this talk, I think I did review last week's talk by Mario, and I noticed that it tends to be fairly software focused. So this one might be a little more science heavy. My hope is that the science heavy aspects of this will help trigger some ideas about, again, the technical side. So I do encourage you all to interrupt if you are interested in a follow-up question or thinking about the implications for the technical questions. Right. So I'm Casey Law. I'm based at Caltech and the Owens Valley Radio Observatory, interested in a lot of these sorts of problems. And the Realfast project is a project that's done in large collaboration with the people you see here, but especially the National Radio Astronomy Observatory, who runs the VLA. So I definitely want to give a shout out to them, because they've supported this from the beginning, because of the sort of tight integration of the computing platform with the VLA computing systems. So let me begin by diving a bit into the fast radio burst science. So that's the kind of the prime science case that motivates the design and the requirements of the Realfast system. The definition of an FRB has sort of evolved over time, because our understanding of what it is physically and how how it's been characterized observationally has changed a lot rapidly. So now I think the best definition of an FRB is that it's a millisecond radio transient with a radio energy, isotropic equivalent energy of about 10 to the 40 ergs, with a brightness temperature of about something like 10 to 35 Kelvin. So those numbers define that space pretty well. And when you look at it observationally, the way it's characterized is sort of shown in this panel, this figure on the left, where you show millisecond sampled frequency spectra. So time on the x-axis, frequency on the y-axis, and that darker colored part with the lines to guide the eye show you the impulsive radio signal. And as it arrives at a delayed time as a function of frequency. So at lower frequencies, it arrives a bit later. And that's an effect of the propagation of the radio signal through an ionized gas. And so what really made FRB stand out is that this dispersive delay, as we call it, dispersive delay or dispersion measure, which is the number we use to characterize it, that number was very large and too large to be explained by any ionized gas that we know about in our own galaxy. So once you leave the galaxy, there's not a lot of ionized gas out there. And so that necessarily implied that it was not kiloparsecs away, as almost all millisecond transients from the galaxy are, but it was gigaparsecs away. So it was a massive change in our conception of what the signal was and the requirements to produce those signals. Another important fact about FRBs is that there are some that are known as sort of impulsive one-off things that just could be cataclysmic in principle, and some of them are known to repeat, as Adam mentioned. And currently there are about 100 events published, or maybe I should say 100 sources published. Some of those sources have multiple bursts, and quite some of them have very, very many bursts. Another point is that there are many, many more that are unpublished because the instrumentation and the telescopes dedicated to finding these things is growing rapidly. And in particular, the CHIME FRB platform in Penticton, Canada, British Columbia, is about to release a catalog of about 500 new events. So it's a highly anticipated result. So the big questions that come up when people have first started to think carefully about what these signals are, and once we got over the fact that they weren't interference, these are astrophysical. So it motivated lots of really creative models and really detailed models about how you can produce those characteristics. So fast, radio frequency, impulsive signals that are have a certain characteristic energy and brightness temperature. And so these are necessarily very coherent processes. So relativistic shocks are a popular model. Magnetars are a popular sort of object to create the emission mechanism. In fact, there might be multiple emission mechanisms that are relevant to magnetars. But magnetars are useful because they're highly magnetized, of course, and you can tap into that energy and produce coherent emission through a variety of mechanisms. There also are a variety of cataclysmic models, so like compact object mergers were a popular early model for explaining FRBs. The discovery of repeating sources sort of made some of those models less popular, but nonetheless, we don't know if there's really one model that explains the whole population. So it's certainly good to keep all of these models in mind. And if you're not sort of a fan of objects that exist, you could always go to the superradiant axion clouds around primordial black holes. So just to highlight the fact that there are some very creative solutions to the FRB problem. So what are they? It's one big class of question, and there are people, of course, all these papers listed here. Everyone there could go into a whole colloquium on this subject, but I'm just very briefly going over it. And then the second class of question that people ask is, how can we use them? And these questions are somewhat coupled. What they are, sort of informs how we can use them. The question of what they are is answered in the most basic sense that we know that they're very far away. And so in that sense, we can start to think about applications. And this is a figure that I like that summarizes all the ways in which people think about using them as probes of the universe. So on the right side is where we are, and on the left side is where the FRB is. So it tries to highlight the fact that there's an FRB engine, so some object that produces the coherent radio burst. There's an environment around that object potentially affecting the signal, the propagation of the signal. As a host galaxy, there's the circumgalactic medium, intercluster medium, intergalactic medium, and all of these things contribute to modifying the signal as it propagates. So I mentioned dispersion measure, which is shown here with this DM. That's the simplest way, which is just a line integral of the electron volume density along the propagation path. But there are also other effects such as scattering So the signal can sort of have a bit of a random walk through space, and that can introduce a time delay. That process also has a frequency dependence. There are also applications related to gravitational lensing, potentially. People have talked about applying this FRB signal to the search for primordial black holes of a particular mass range. Is another interesting application for FRB propagation, inference of the path of propagation. And one really cool thing about this, just to quickly note, is that one of the first results that have come out already just in a high profile paper last year is that we've already shown, we, the FRB scientists, have shown that dispersion measure correlates with distance. So for the FRBs that we know exactly where they are, we can show that dispersion measure is proportional to distance. And that's actually a direct relation, that's a direct cause of the fact that there is baryonic matter in the intergalactic medium that we are measuring. So all of that science, as I implied in that last comment, relies on the fact that we can actually measure distances to these objects. Because if you measure just a dispersion measure, a line integral or a scattering measure and all these things, they're all sort of line integrals across this path of propagation. So that problem is still very severe for radio astronomers studying these bursts. And so here's a little corner of the Hubble Deep Field. If you find use a single dish telescope like the Parkes Observatory, which is the place that the first identified fast radio bursts, they have a localization precision of about this big on the sky. And no one would sort of assert that they can identify the home galaxy of this particular burst. It's very ambiguous. Even the Arecibo telescope, or say the FAST telescope in China, have a pretty ambiguous association. But the VLA, the synthesized beam size now of the array, is actually small enough that you can say something very, very precise about its location, and also very robust about its association with counterparts. And so the point is that interferometers are really going to be the best way that we can identify FRB host galaxies. Once we have that, we can start to say really we can characterize physically what's happening, right? So instead of talking about like the fluence, we can talk about the luminosity and so on. So that's really the motivation for a lot of the work that we're doing with interferometers and FRBs. A demonstration of that here, here's 3 panels that show the detection and localization and association of a burst with multi-wavelength counterparts. And this is all VLA data towards this FRB known as 121102 that Adam mentioned. And on the left is, again, that dispersed pulse. So this is how it's detected as we search over use a set of matched filters to search over this space of delays and times. Once you've identified and you cut that out, you can make an image, which is shown in the center panel. Now you know exactly where that impulse signal came from, and then you can cross-match that to deep optical images or radio images. And in this case, we found a luminous radio source sitting there, coincident with the bursting source. And we can measure its spectrum, we can characterize it. We can talk about the nature of the emission that comes persistently, in addition to the nature of the coherent emission. And then also the optical counterpart shown in blue there is we have a spectrum of that source, and we can say exactly where it is, right? So we have a distance. And that it's an amazing package of things that we measured with that first localization, and demonstrates all of the things that we're trying to do now in a really automated fashion with a new set of telescopes and techniques. So one final point on the science before I go into the technical side. There's a lot to explore here in terms of like the origin, and one thing I'm trying to pursue myself is thinking about the connection between multiple classes of transient. If we have a pretty good physical picture of where FRBs come from, we think about, we can also think about how they connect to other classes of transient, right? So we know it's extremely energetic phenomenon. It requires a very peculiar kind of object to generate that coherent emission. That object is born in a particular kind of place. It looks a particular way when it's born. And as it evolves, it might even affect its environment. The remnant that's there might affect its environment in a particular way. So this is the alphabet soup on the bottom here shows various acronyms for classes of transient and peculiar, subclasses of magnetar. which may or may not be connected to fast radio bursts. But we do know actually one case, actually, can you see my mouse? Perhaps not actually, but soft gamma repeaters on the bottom right there are indeed now directly associated with an FRB burst in one case. So there's a soft gamma repeater in our own galaxy, which was seen to produce a lot of high energy emission during a sort of a storm or a series of bursts last year. And one of those bursts happened to be associated with a radio burst that had a luminosity comparable to the fast radio burst luminosities. And so there's already one connection between those two different classes of objects. But there's still a whole kind of range of interesting questions about what happens when you think about what that object looked like when it was born. Maybe it looks like one of these superluminous supernovae. Maybe it's a fast blue optical transient or what have you. So that's a really fun area to explore, I think, in terms of what is the origin of the object. So that yeah. So let me emphasize that point. That's the reason I mentioned that all the science and in particular this slide is this picture. It might also inform all sorts of creative ways of thinking about the triggered, rapid response observing and coordinated observing techniques that I know the SCIMMA group thinks a lot about. And so there are great specific questions you can ask when you have a physical model like this in mind, and that can inform your follow-up strategy. So coming back to Realfast, so we are interested in pursuing this problem again because the VLA is an incredibly sensitive radio interferometer, and we knew that we had the ability to add computing power at the telescope to do a new kind of analysis. And so that was basically our strategy. We came to the NRAO and we proposed constructing a dedicated computing platform with a custom software pipeline for doing fast radio bursts and other kind of millisecond transient search. So the key features are its millisecond imaging, real-time processing on a GPU cluster, and commensal operation. So it's taking a copy of the primary data, a fast copy, and then doing analysis on that in parallel. And then fourth here is we have automatic classification and alert systems now built for Realfast. So technically, on the development side, just to summarize, this is sort of one of these spaghetti diagrams to show you the flow of data. So the top half of this diagram kind of shows the primary data flow of what we call the production of what we call visibilities for radio telescope, and that's what the primary data product that goes to the observers out through the internet. So there's a second scale sampling of this data product that is distributed to observers, and that has a data rate on the order of tens of megabytes per second, typically. What happens in the middle part of this diagram is there's a distribution of data to the bottom half, which is the Realfast system, and that's a fast copy of that data. So before it's integrated in time, you can copy and send that data off to our dedicated computing, and that data product has a sampling time of about 100 to 1,000 times faster than what the primary data product is. That allows us to access the science we want at the millisecond cadence. So the overall, situation for Realfast now is that it's fully installed and is operating commensally. It's fairly reliable. Things are more or less meeting their planned scope. And we have data capture working, and the search system is working. We have data products that we're recording regularly. And we also have this automatic classification of every candidate transient for a classification in a data quality sense. So not identifying a source class, but identifying good versus bad candidate transients with a latency of a few minutes. And that's done through this fetch classifier, which is a convolutional neural network. If you're interested in real-time data quality and classification for radio telescopes, you can check out this Agarwal et al. 2020 paper in MinRAS. So that particular component is really important, I think, for the kind of connection between radio telescopes and SCIMMA and other platforms, as I'll refer to later, because one of the traditional challenges of radio telescopes and automated analysis of radio data is data quality is very poor in general. that's because we have lots of interference from cell phones and radar and so on the ground. So these data quality classification systems are generally designed to remove those bad candidates, which can sometimes look quite similar to astrophysical events. Observing status. This is a plot of accumulated observing time as a function of time. So days are on the x-axis and accumulated time on sky is on the y. We sort of turned the system on for internal testing in June of 2019. We really first deployed the commensal aspect of it in August of 2019. So that's when you start to see the ramp up of accumulated observing time, because those are observing configurations that the typical user could use to schedule time without any connection to the Realfast team. So that data started flowing through the system. And then in June of 2020 was when we had a lot of time on sky through this VLA sky survey, which is a new multi-epoch all sky survey that's under sort of 3 different epochs. And this is the commencement of the second epoch in that June 2020. And that's when we had a nice big ramp up because we were fully integrated with the VLA sky survey. And so we got lots of time on sky during that survey. And we're up to 90-ish days of observing time on sky, which is about 50% of all VLA on source time. We have ideas of how to expand that, but that's actually, we're pretty happy with that number. And in total is about, a few to several petabytes of visibility that have been transformed into images and searched for these transients. And so this characteristic timescale is about 10 milliseconds typically. For most fast radio burst or pulsar surveys, that's considered pretty slow. So typically you'd like to be about 10 times faster, and that's one of our goals, is to push up the data rate and through the system and improve our sensitivity to those millisecond impulsive signals. So let's give you a sense of what's novel about what we're doing. We don't control where we point or what frequency band we observe in, but that does mean we get somewhat novel selections, right? So there's potential for someone observing, say, a known supernova, and then maybe perhaps it has some sort of magnetoid remnant that's sitting that's been sort of created, in that event, right? So there's potential for us to find things sort of coincidentally that way, and I'll mention an example of a source we found coincidentally in that fashion. And then we're also observing at novel frequency bands. Typically, people like to maximize field of view to improve their chance of detection, and that argues for going to lower frequencies. But we have tons of time at S-band. This is 2 to 4 gigahertz. That's where the VLA Sky Survey is. We also have a fair amount of time at these higher frequencies, which is very uncommon for surveys. And so there's potential for us to discover events there that might potentially look different from what people have typically discovered. And then one other cool thing is that because we're commensal, we actually can have simultaneous slow and fast observing, right? So we can find bursting signals and localize them, characterize them. And then in the same data stream, we can actually make images that are from the slow data that are deep and sensitive, and can find potentially persistent radio sources that are associated with the fast bursting source. And I'll show examples of how that's worked for us also. And then finally, there's this minute latency alert system that we get, where we get classified high quality alerts distributed within minutes. So I can give an example of that. And I know it's a particular interest here, so I wanted to highlight this with its own slide. So in January AAS last year, back in the days when I could go to AAS, I had managed to connect with Aaron Tohuvohu, who's at the time he was a grad student at Penn State. I guess many people here potentially know him, maybe, I don't know. But he's now a grad student, sorry, he was a staff member at Penn State working with Swift. Now he's a grad student at Toronto. And he reached out and said, hey, it would be really great to collaborate on this. We've got this great system called Guano, which is a way of triggering Swift BAT and also a general Swift pointing to respond to alerts with very low latency. And no one had really done very low latency triggers for FRBs before. There's been a lot of effort to coordinate observing. In fact, there are simultaneous observations of high energy telescopes and FRBs, but the triggered side of it is not so well demonstrated. So we reached out, we collaborated, and we managed to set up a fairly rudimentary, pretty quickly, I would say, system for sending out XML files, so a VO event file to the Guano system to trigger Swift observing. And so the idea is to two things. One is trigger the recording of a buffer of BAT data. So that can be simultaneous with the FRB event. And then at the same time, the goal is, if it's particularly compelling, we can then trigger the slew of Swift to observe with XRT and UVOT within tens of minutes. And so on the right side, I show the timeline for this particular FRB candidate we had in the middle of last year, where we were able to classify and identify the event within a few minutes, send the notice to Swift, to Guano system, and based on the location of the satellite and availability, we were able to trigger the recording of that. In this particular case, it was available. We had that buffer saved. We also were able to repoint the telescope and get on the target within 32 minutes, which at the time, I think, and then maybe even still, is the fastest response to an FRB. In this particular case, we had a reasonable confidence that it was an interesting candidate, but we didn't actually know it was an FRB. And upon further investigation, it looks like it's probably just a false positive, actually. So false positive in the sense that it was, we set the threshold fairly aggressively. And so like a thermal noise kind of deviation is actually potentially the cause of this, which is not uncommon for fast radio transient surveys where you have literally like billions and trillions of samples you're taking from this population. And so you have to have 8 sigma or even 10 sigma thresholding to remove any chance of a false positive of that nature. It wasn't interference, we think. It's probably just noise. But the point is that it demonstrated the system very, very well. And so that we felt like that was definitely motivation for publishing. And so that was, it's on the archive now if you're interested. Actually, I could pause here in case, I think this slide connects well to what people are here interested in. If there's any questions, I could answer them now.
Casey, I wondered, are you using, so the XML, we're using the FRB event that was sort of designed out, some folks out in Amsterdam. That's
right. Yeah. It was the FRB VO event format, and in fact, the Amsterdam group also, and that was actually, I think I was on that paper, has a framework called Comet, which is a way of just setting up the broker system.
Well, and is that being used? I'll give us to Derek in a minute because he has a question too. Is that being used by many groups now, or is it still growing?
It's still growing, and I think the Chime group is actually just about to deploy this with the Guano team, so I think they are also using it. So it's doesn't have a widespread adoption, but it is sort of sufficient for FRB purposes because the event rate is quite low.
Yeah. Yeah, that's what I was involved in some of the discussions at a low level. That was my thought as well. I see Derek Fox has a question.
Hi, Casey.
Hi.
Yeah, this is really great stuff. My question was, and the connection to SCIMMA and Hopscotch, do you have observers lined up to trigger off of your Realfast detections other than like the Swift BAT? And are there mechanisms in place to follow up if somebody sees something interesting after triggering on a Realfast detection?
Yeah, good questions. We don't have, yeah, I would call this a demonstration. So we have not planned very extensively around this, but I would like to think more carefully about it, and which is part of why I'm here. And so if we found something interesting, we probably would have had to chew on it for a while, and we might not have got all the value out of it, right? So if it was a transient signal and we wanted to rapidly follow up, we wouldn't have been able to do that. But I'm interested in thinking about, exactly the sort of the trajectory of follow-up operations, in that diagram I showed with, all the different phenomena, right? Different optical transients, high energy transients, and radio transients. And there are many ways in which the signal might manifest itself. And it's not clear to me what is the highest value strategy for following up. But I think the easiest one to implement is this. So radio signals can be classified. You get a rapid response, and the physical scenario is that you have something like a soft gamma ray, repeater that's active for some period of time, and that's caught at both windows, at both bands.
Oh, absolutely. So this one turned out maybe to not be a real FRB. Do you have an idea of how accurate your real time classification is?
There, yeah. So if you do go to, let's see. So the Agarwal paper has a lot of detail on the classification quality. We've applied it pretty widely now for some time, and I think we're finding there are some false positives. Maybe it's hard to actually assess machine learning algorithms, well in a theoretical sense. So I think I don't have a sort of a quality number or a precision number, but it's definitely good enough that when you combine it with simple thresholds on, say, strength of the signal, and some other kinds of filters on bad interference, we've actually gotten to the point where we're willing to turn this on. The guano trigger system is turned on right now.
Sure.
And we're not worried about false positives so much right now. We had sent, I'll be honest, we have sent some bad triggers.
It happens. So does LIGO, by the way.
Oh, good.
Yeah. All right.
I'm in good company. Right. So yeah, so that's a great connection to everything you people have thought very carefully about. Yes, good. So turn back to science for a bit, and then a couple of, after science, I'll have a couple of slides to think about next steps in the future. So the Realfast system has been, as I mentioned, observing for since the middle of 2019, and we have a number of detections, discoveries, results that we have either published or working on. The one that I've highlighted pretty well already is this, there's a prototype version of this system that was involved with the FRB 121102, and that appeared in a series of publications in 2017, that top panel you've seen before. There's another result that I published, maybe it was 2 years ago, on benefiting from this simultaneous fast-slow observing. So FRB search at the same time as we're looking for slow transients. And so in that case, we had a science target, which was these superluminous supernovae, which are relatively old. And the argument is that the optical, characterization of the supernova is consistent with that it's powered by a magnetar spin. So like there's some formation of a magnetar, and then that's the spin down of this extremely magnetized, fast spinning object is partly powered, explains the extreme luminosity of the optical transient. And so if that's the case, then you can look at late times when most of the ejecta is optically thin, and you should see that magnetar emerge as potentially as a radio transient on slow time scales, and potentially as a bursting transient as an FRB. And so we targeted a sample of 10 of these objects, and we did not find FRBs, but we did find a very weak detection of the late time radio emission from one of the 10 superluminous supernovae. And this is actually, I should also add, there's a second paper on this by Taraneh F. Takari, who Peter knows well, who's done this, excuse me, who's done a similar experiment at actually a much grander scale, and has confirmed, we have consistent results. So I shouldn't say she's confirmed my results. She published her paper first, but I confirmed her results. So that's kind of a fun application of the fast-slow science. There's also RAT searches, so these sort of intermittent pulsars that are potentially connected to pulsars. Well, I mean, they seem to be a class of pulsar, but it's not clear if they're an exotic class of pulsar or not. And so we have a work where we are detecting individual pulses from these sources, and to use that for timing purposes and to measure spin down and associate that class with the classic diagrams for classifying pulsars. So I put this in a slide called non-commensal discoveries because we were controlling the telescope in all of these cases. And then here's a slide on more commensal discoveries. But in this case, it's a slide just for galactic things that we've discovered in a commensal fashion. So one was when we first turned the Realfast system on, someone happened to be pointing at the galactic center. And we found a pretty bright, highly dispersed transient really right away. We got really excited because it's a dispersion measure of 1700, which is like much larger than the typical dispersion measure you see in the Milky Way, but is not anomalous when you're looking at the galactic center, of course. That's actually quite normal for the electron column density you expect to the center of the galaxy. So while it's not an FRB, it is, and it's in fact a rediscovery of a known magnetar, is fun because it demonstrates that the system works as we expect. And so we put out an ATEL on that one for fun, basically. And then the middle bullet here is that we have a result in the works, which is we've identified an impulsive signal commensally during an observing campaign in which people were using the VLA to observe the fields of unidentified Fermi sources. So there's a whole sort of cottage industry of trying to take the Fermi catalog and classify every source, but there's a whole set of them which is unclassified because we don't know exactly what the counterparts are in the radio domain or the optical domain. So people survey these fields, look for, say, spectrally peculiar radio sources, and have complex inferences about the association with the Fermi source. In this case, they were observing this field looking for radio sources, and then we found an impulsive radio source. And so that implies that we probably found the source, the compact object, the neutron star that causes the Fermi emission. And that's work in prep. So we think it's either a young neutron star or potentially a millisecond pulsar. But we're not quite through the analysis yet to distinguish between those two big classes. And then third is that, again, I mentioned the VLA Sky Survey recently completed its second epoch, and on the bottom right, I'm showing the pointing locations of VLAS in the second half of the second epoch, so half the sky, and the red points show pulsars, known pulsars that were discovered at that time. So in that survey, so about 26, I think, known pulsars were rediscovered or redetected. And there's maybe some value in this because it's a new band. We're also localizing them precisely, which is not typically the case. So we have some ideas for how to enhance, the catalog of known pulsars. And then back around to FRB science, this is really what's motivating so much of what we do. We have quite a nice selection of results now after our first year and a half, 2.5 years of observing. So one is our first FRB discovery, which is 1906 14D. This was discovered, and actually it was in collaboration with the CHIME team to follow up a repeating FRB. But in fact, this was discovered sort of in the background, if you will, of the target we were looking for. So it's kind of like a commensal discovery. It's a coincidental FRB in the background on a higher dispersion measure than the target source. And we localized it and found that it was nicely associated, reasonably well associated with the host galaxy. That host galaxy turns out to be quite hard to measure a spectroscopic redshift for, but we have a rough photo Z which is consistent with the dispersion measure. And so we've argued in this paper that they're likely associated. Another example is FRB 1809-16, which is perhaps more widely known as the periodic FRB. So it's a very active bursting source in which the episodes of bursting have a period to them. So on the order of weeks, and that so it's not a millisecond period, but it's sort of a longer evolution, longer time scale period. And we were able to we were looking for bursts and didn't find the bursts, at least initially. but we were able to, because we spent a lot of time looking for bursts, we actually had a very deep map of that field. And so we were able to put a limit on the persistent radio counterparts to that bursting source. There's also FRB 1803.01, which is a localization. So that's a collaboration in which we follow up a localization by another telescope and found a burst, and we're able to localize it to arcsecond precision. And then we have a similar story for FRB 0520, which I think is one that is going to be making some more news soon. We don't have anything published yet, but it's a discovery from the FAST telescope in China. And they reached out to us because they found it was a very active repeating source. And we targeted it and went from sort of went from the stage of chatting in the hallway to writing a DDT proposal to getting on Sky and detecting and localizing it within a couple of months. And it's turned out to be a really fascinating source because not only is it very active, but it has a luminous persistent radio counterpart. So that makes 190520 quite similar to that of 121102. And it's only the second known example of an FRB with a persistent radio counterpart. So that's something we're working very hard on right now. And then there's actually another result, which is pretty hot off the presses, and I can't share yet, but we have another source which has been localized now. And the theme here is that we're not finding a lot in terms of commensal discovery, because the field of view of the VLA is relatively small. So that's always been true. We won't be finding tons of FRBs in that commensal form, but when we are targeting known repeaters, we have been quite effective. And that's, I think that will continue to be the case. And here's a little slide, what's the word? Little postage stamps, that's the word. Postage stamps of, the different measurements we've made. So the top row is all the dynamic spectra, so frequency versus time for 4 of these that I mentioned. With that, you cut out that little center of that dynamic spectrum, and with the interferometer, you can make an image. And so we have burst localizations. You can also take the deep slow radio data and make a deep radio image. And in that case, generally you see nothing, but on the right column, on the third row, you see a persistent radio source for 190520. And then on the bottom is you take that same localization, and then you can look for optical counterparts. Of course, I could have added another row of high energy limits. We wouldn't be so complete in that row, but 190520 has high energy limits. 180916 has high energy limits. And so we'd like to be able to expand this and use our localizations well. So predictions, as I mentioned, the VLA, so I should explain the plot. So one nice way to characterize the discovery space and the value of an FRB search is through comparing the detection rate, which is shown on the x-axis here, against the localization precision on the y. And generally, your radio interferometers have an inverse relationship between they have an inverse relationship between the area, the size of the dish and the localization precision. They also have an inverse relationship between the precision of the localization and the computing requirement. So very precise localizations require searching lots and lots of data. And so that's why you tend to have points that lie either on the bottom left of this plot and they might tend to go to the right side where high rates of discovery for very poor localizations. And so that's where CHIME sits, for example. So the VLA's value is really not in discovering in an unbiased fashion the FRBs. We're always going to be finding very few in that way, but in targeting known repeating FRBs, I think there's a lot of value and a lot that will come out of this effort. Yeah.
And then, Casey. Yeah. Sorry, Casey. I just wondered, were you on that chart? I see you have DSA 10. So the proposed DSA 2000 is also going to be an FRB machine. Yes, absolutely. And I'm actually very heavily involved with DSA 2000. And actually, I'm remiss in not showing DSA 110, which is an actively being developed
And you know, I have many telecons a week on that, so I should show 110 on here at the very least. So 110 would be, yeah, roughly an order of magnitude to the right of DSA 10, and somewhat down in this plot, so somewhat slightly better localizations. So it's in a very nice space. It's actually pushing to the bottom right, which is really good.
Right.
Okay, and I should say that, you know, all the points of these boxes in this space is actually very, you know, sort of flexible. There are some parameters on the bottom where you have to assume populations, you have to assume spectral indices and so on, and power law distributions of the flux densities and so on. So these are not hard numbers. Yeah, okay. And so my last slide is just thinking about the future, and where we'd like to go in the future is, you know, in the terms of development of our capabilities, we'd like to improve the classification quality. You know, I said it was good, but we really don't want to be sending out, you know, high value, you know, sending high value satellites to go look at terrestrial or interference. So we like to continue to push on that. We have this fetch classifier can be expanded to include not just the dynamic spectra for identifying interference, but also the image domain, right? So that's something novel that the VLA has, is you can simultaneously classify based on those two kinds of data. And we're also working hard on automatic sort of archiving, ingestion, and management of the data we produce. So every candidate that's detected by Realfast triggers the recording of a little bit of the visibility data, and that allows anyone to reproduce that candidate and do science with it. So we're going to, in the next 6 months or so, we're going to sort of formally hand off operations to the NRAO. And that should, in the process of doing that, we will have to have an automated form of managing data and allowing the NRAO to manage the operations. And science-wise, you know, we really want to push to having more time on sky and faster samples. That's the big ones, get us more sensitivity and more potential for discovering events. And then just dynamic VLA is a phrase that I've been thinking about a bit, which is very much connected to what SCIMMA is interested in. So thinking about the connections for alerts going out, alerts coming in, you know, co-observing, all of these things I think are related to things that you are interested in. And I just wanted to highlight with this panel on the left is that the Realfast is not the only commensal platform at the VLA. There's also this VLite project, which is uses a different receiver that's actually effectively always on sky. So the low frequency band of the VLA is around 380 megahertz, I think. And they have both imaging, very nice imaging ability, and they have a fast transient search capability there. And so they've already made an FRB detection with that system, which is shown on the bottom panel here. That turns out that system is not a localization; it's just a detection with a pretty large area in the sky. But I think they have an interest in improving that also. So there's a lot of commensal capability at the VLA that I think should play into this question of the dynamic VLA. How do you plan around, you know, novel physical scenarios and novel physical mechanisms when you have simultaneous coverage at fast and slow timescales at high and low frequencies? So that's an interesting question and a problem I'd like to think about more carefully in the future. And with that, I will stop here.
Great. So while people might be thinking of questions, actually, I'll go straight to David. David has a question. David Kaplan.
Yeah, okay. Thanks a lot, Casey. That was really interesting. So I guess, you know, I have a couple questions. One is, you talked about being more careful with your classification to generate smaller numbers of false positives for sending out, but I know that a number of the people on this call like to play with larger samples of, you know, slightly dubious origins that can cross-correlate. Is that, you know, some sub-threshold game that you think could be played? You know, if you're not slewing Swift yourself, but you're at least, you know, saving and archiving and sending these things out to be cross-correlated against, you know, neutrino signals or things like that. And then, you know, looking forward, you know, as you say, DSA 2000 will be if it gets funded, will be quite powerful, and there are going to be a number of other similar facilities. Are there any sort of joint technologies or joint requirements that should be set up now to, allow things to proceed with much larger numbers and much, higher data volumes, both in and out?
Right. Well, on the first question, one thing that pops to mind is that, we have thought a little bit about sort of subthreshold coincidence between Realfast and VLite. So, on this slide, we know that they find things and we find things that we're not quite sure about. If we both found something that was 5 sigma, deviation, we'd like to, we would like to, let people know about that. So that's one example. In terms of
even high energy triggers, in terms of some of the SGR work.
Yeah, that's actually that's a really good example of how that could work. And so we have not, we have generally tried to be pretty conservative, mostly because, as you know, the distribution of significance of an event is
highly non-Gaussian.
It's not Gaussian, yes, exactly. For radio, especially for radio data, I think. But we're getting better and better. So I think there is an argument to be made for being more liberal in sending alerts, maybe in some some organized fashion where you let people know what they're getting. Yeah, so that's a great point. We should think more about that. And on the second point, well, DSA 2000 is especially novel in the sense that it's not trying to distribute, this sort of terabyte per second data stream to the general science user. It's really has a focus on taking the things that we know how to do well with radio interferometers and integrating it into a single pipeline. And the goal is to actually distribute either images directly to science users or even catalogs, potentially. So it's really trying to be sort of like the Roman telescope, or the sort of where the optical community is today, and it's trying to do that in the radio domain in the next, say, 5 years. So we do need to think, we do need to be smarter about how we manage that. And I think we're going to be probably, for the most part, following on the coattails of the optical community, probably, and the LIGO community. But I'm not sure what more to say that's intelligent in that regard. Other than that, we have a lot of work to do.
Yeah. So Casey, when you were showing the Swift sort of follow up to an FRB trigger, I think you said, so it was 32 minutes from the observation being made to Swift being on sky or on target. How much of that is sort of, how much of that time budget is within your control? I noticed you send the notice 6 minutes. Is basically after 6 minutes, it's no longer in your hands. Is that right?
That is correct. Yeah, I think there are a couple of this paper, if you read it, I think has a couple of more, just a little more description. And I think some of it was, Swift operations requirements. Naturally there are some checks and some things there. I'm trying to remember if we actually had a phone call for this one or not. We may have had a phone call in that 23-minute gap there. There may have been a phone call. So it's not streamlined yet. There are definitely ways to make that much better. And I think Aaron's goal is to actually have reliable sub 30-minute repointings.
Okay, and so from the bit that's in that first 6 minutes, that's in your within your control, is 6 minutes what you think is that your target, or are you aiming to reduce that? Because some telescopes may be quicker to respond as well others. Yeah,
I mean it. Is that fast or slow? I think is a interesting question. David's worked very hard on doing smart things to be much faster than 6 minutes. In our case, we we designed this for high throughput, but not low latency. So those things are not always the same. And so we have sort of a distributed job scheduler where we actually sort of multiplex the data in time. So we have little time packets that we send out for sort of a single node or process to chew on. And so that gives us a lot of flexibility in the processing, but it means that you only really have one server doing the analysis on one chunk of data. That makes the latency longer. So we have it's more reliable. It scales well over a cluster, but it adds a latency. And so it's hard for us to actually squeeze that down unless we know exactly what we're looking for. One way to squeeze it down would be to deliberately define the pipeline to search for low dispersion, for example. So if we know it's in some limited parameter space, we can just search for that.
Okay. Yeah, I see Peter has a question.
Yeah, hi Casey, nice talk. I guess following up what David was asking a little bit, in terms of the work that we need to do, I would say, that I think this, a lot of it is software engineering, is figuring out how to handle these data streams, especially in radio astronomy, especially in this kind of real time. I think we've got tons of work to do there. So once we get out of the correlator and past the kind of radio astronomy specific stuff, and we've got our stream of FRB VO events or whatever, do you see any major software bottlenecks there, or do you feel like that side of the equation is pretty well developed at this point?
I don't think there are real serious bottlenecks there. I think this timeline sort of highlights that. I think most of the difficulties are in the data classification and sort of robustness to interference. That's always going to be a big problem for us. But again, the event rates are so low that I don't see any serious problems there. I don't see any, because the data rates, the event rates are so low, I don't see big problems with like distribution or interpretation of, downstream things. I think someone like LIGO has basically solved all those problems for us, right? Because we already have much more precise localizations at a very low data rate. So I don't think it's challenging to consume or interpret our data. I think that's true. But I think it would be good to, define that question better, like what can we do today to actually test that assertion, right? Is there, maybe it's low latency, high energy triggers to satellites, subthreshold, maybe that reveals some pressure point that we haven't thought about yet. I don't know.
Okay, we're about on the hour. Thanks very much again, Katie. That was really interesting. I actually have a ton of questions I may follow up with online, and I know we're both in the general penumbra of DSA 2000 as well.
Yes.
But yeah, that's really very interesting, and this will be up on YouTube probably later today or by tomorrow, and I'll send out a link to the Google group when that is true. I just wanted to revisit the white papers question. Well, we're going to be releasing these on about a 2-week cadence. You can see the current state of them there, but during that 2 weeks, we'd like to have them reviewed. So please do have a look at those. So thanks very much, Katie. We'll be having another public talk next month, which will be announced by the Google group. And I hope you all enjoy the rest of your day.
Thank you.
Thanks, Casey.
Thanks, everyone.